Let's do a short recap of what we just covered in the last 7 minutes. So, the converter is required to be perfectly efficient. So, therefore, all the elements that go inside the converter must also be perfectly efficient, which means that all of these should have 100% efficiency. So, does it mean that if all the components are efficient, the entire system is bound to be efficient? Well, not quite, but if the entire system has to be efficient, then each of the components must have to be efficient. You can analyze this statement in whatever angle or aspect you want to, and you still find that the reverse argument is always correct. The obvious candidates for lossless elements, as we know from our basic electrical engineering studies, are the capacitor, the ideal capacitor, and the ideal inductor. So, it doesn't come as a surprise when we show those two elements as obvious occupants of the power converter. The switch, however, is not so widely spoken of, and that's because everywhere in the classical study of electrical engineering, the switch is treated as a given. You probably might have done 10 pages of analysis, and the whole analysis started off with just one line: when we switch on the supply, the voltage is applied. And that's probably the only mention of the switch. Till at the end, you probably somebody says that okay, now we have done our job and let's switch it off. So that's the actual mention of the switch that happens mostly in most of the classical study of electrical engineering. So we included the switch as one of the essential components of a power converter, and therefore by the logic that we used previously, we would expect that it is a lossless element. The ideal switch is of course a lossless element, because in its stable state, whether it's in the off or the on state, either the voltage or the current is zero. So the instantaneous power in each of the stable states is zero. So that's not a problem, that part is fine. But there is also another part of the operation of the switch, which is the transition, because if the switch is permanently in the on state or permanently in the off state, we wouldn't have required the switch at all. So it is required to switch or transit between the on and the off states. So what happens during these transitions is also important. Now see, the integral that is shown there, that shows the energy which is absorbed by that switch when there is some voltage across the switch and some current through the switch. Now that is a general formulation. We will see more applications of this general formulation later, but this is true for any element, not just the switch. So Vs and Is generically represent the voltage across the switch and the current through the switch respectively. Now once we integrate this product Vs Is from an initial time t0 to a final time t0 plus delta t, where delta t represents the transition time. Now this integral is non-zero if delta t is non-zero and Vs and Is both are non-zero, and of course finite, bounded. Now if delta t is 0 and both Vs and Is are bounded, then this integral is uniquely 0. Okay, so that's the fundamental theorem. So that's where the switch gets its lossless property from. It is lossless in its on state, lossless in its off state, and lossless during transitions. Okay, there was something more interesting that we saw in the previous video, and that was if a current step is applied to an inductor, then obviously we will have to find its derivative, which creates which produces a voltage across it in the form of an impulse. And similarly, if you take a capacitor and just apply a voltage step across it, then the current through it will show an impulse. Now, in both these cases, note that we are using the derivative forms of their governing equations. Now, we want to create a converter which has its variables bounded. We do not really want any impulse behavior in any of the voltages and currents. If we got to do that, then we must ensure that no current step is applied to an inductor and no voltage step is applied to a capacitor. But the converse is completely possible. Check that we can very easily apply a voltage step to an inductor and a current step to a capacitor. None of these two creates any impulse output behavior from these elements. So the trick is to ensure a certain circuit formation rule which takes care of this fact and never allows a voltage step to a capacitor or a current step to an inductor. It always ensures that a current step is applied only to a capacitor, and if a voltage step has to occur, it is applied to an inductor and only an inductor. By now you might be wondering why we are obsessed so much about the step function. Where is the step function coming from? I mean, normally in AC analysis, AC circuit analysis, we didn't really bother about the step function, right? For example, when we studied phasors, who cared about a step function? We only bothered about sinusoids, steady state. But look, as I was talking about, the switch in classical electrical engineering is pretty much an ignored element, right? Whereas in power electronics, that is the principal player, okay? The rest of it, all the other elements, they don't appear to be that smart and intelligent when you compare it to what the switch does in a circuit. So, when the switch turns on, what it does is it equates the voltages of the two nodes across which the switch is connected. Also, when it turns on, what it does is that it sends current from one part of the circuit to another part of the circuit. So, if the switch is connected to a voltage source on one side, then when the switch is turned on, the other node of the switch is automatically brought to the potential of its other node. Now consider if the switch is connected to a current source, that means the switch is in series with the current source, and the current source till some time t0, it was sending its current into some particular element, and when the switch turned on, part of the current was diverted through the switch. So basically, whatever circuit was connected to the other end of the switch will see a current step. In the earlier case, what we talked about, the switch node actually might have seen a voltage step, because when the switch was off, we really don't know what the other node voltage was. It could have been anything. I mean, if the switch is off and it is ideal, then the two nodes of the switch could be at any arbitrary potentials which are completely unrelated to each other. So the presence of a switch makes it imperative that there will be step functions applied to several components inside the converter circuit. Now those steps could be voltage steps, those steps could be current steps. Now we'll have to see how the switch needs to be connected along with the inductors and capacitors and other sources in order to give us a stable operating circuit which has no impulse behavior.